Okay, this is our first video lecture in the middle of all the chaos, period. I hope everyone is doing well, period. This morning I spent hours trying to make a video upload to YouTube, only to find out the volume was too low, period. Now I'm using Photo Booth on my Mac, and I think it's going to work much better, period. In order to prepare for the video, you need to have the notes printed or at least open in a separate screen. You can also take notes in your notebook as we go, period. You need to have your cheat sheet, which you should have already printed out. And then one of the handouts I gave out before spring break, and I have loaded to the Mayhem module, is a handwritten summary. Have that out also, period. Before spring break, many of you missed that Wednesday's class. So please remember, I have loaded the brief lecture notes from that class with the 2 examples that we did. You definitely needed to have done handout 9, all of number 3, 4, and 5 before you watch this video. 2, I've lost my eraser. To recap, to be able to compare what we're doing on this video, the Wednesday before spring break, we did sampling distributions. We talked about the difference between X and X bar, but no matter which one we were doing, we were going to get z-scores and then get areas, and that whole process went forwards and backwards. X was technically test 2 material. X bar was technically test 3 material. We talked about what the mean and standard deviation of X bar is. We also talked about the normality criteria. Just so you know what you have to memorize and what you do not have to memorize, this is the cheat sheet you will be provided on test 3. If you look down here at the bottom, this is our sampling distribution stuff. We'll get to all of that in the upcoming weeks. That is what we did that Wednesday before break. The X bar, the mean is mu, standard deviation is sigma over square root of n. You'll notice normality criteria is not on here. You do have to memorize that, period. This thing over here with the p-hats and the p's, that's what we're doing in the video today. So again, when you're doing your homework, keep the cheat sheet out so you will know that these formulas you don't have to memorize, so that way you don't forget what they are. Now, if we were in class, I would ask 5 of you students 2 brief questions as an introduction. Let's pretend. How much coffee in ounces do you drink daily? Let's say that was the question, okay? Some student might say 20, another student might say 22 ounces. Maybe I have a student who doesn't drink coffee, they would say 0. Maybe another student says 10 ounces, and another student who does not drink coffee says 0 ounces. This is numerical data. They answered my question with a number. These are the individual x's. Of course, I could calculate x bar, add them all up, divide by 5. I would have a sample mean. That's the stuff we did before break. That's the stuff that I call x bar, mu, because we could use the x bar to estimate mu, stuff like that. Today, even though we're doing sampling distribution, it's really for if you want, we'll call it categorical data. Let me ask a coffee question, but slightly different. Do you drink coffee daily? So maybe that student said yes, that student says yes, that student probably would have said no, that student would have said yes, that student would have said no. You can't add up yeses and nos and divide by 5, right? You can talk in proportions though. Let's see, 3 out of 5 or 0.6 or 60% drink coffee daily. So the things we're doing today, you're going to see fractions, which are decimals, or you can turn it into percent form. These are proportions. On the next sheet of paper, I'll introduce you to the notation. But this is what I call my camps. And this idea of figuring out what camp you're in is going to take you all the way through the final exam. So let me just show you this piece of paper. You can read it later after the video, but before break and then today's video, it's all this material. That, the top part, we'll get to in the next video. This is a summary of what we did before break. This is going to be a summary of what we're doing on the video today. So the difference between measurement camp and proportion camp. All right, so I'm pretty much going to follow along with the notes. Let me put the old notes away. And I will be writing the stuff on the board, pretty much just like you see in front of you if you printed the notes. So we do have some new notation you may not be familiar with. So this is called the sampling distribution of the sample proportion. Like, for example, I had, what did I have? 60% of students who drank coffee daily in my example just a second ago. That would have been the sample proportion, 0.6. All right, P is the population proportion. There are a lot of P's in statistics. It's not my fault. If you take it in context, it will make sense. P hat is the sample proportion. We use the sample proportion to estimate the population proportion. We use P hat to estimate P. Now I know a few of you like to go to Khan Academy or Google on the internet. This P for population proportion only became popular probably 15 years ago. When I was growing up, the population proportion was denoted as pi. So just in case you ever see pi in this topic, it's not 3.14, you'll know that that was just old school notation for population proportion. All right. I'm not going to go back through all of the background of what sampling distribution means. We did that before break. We pretty much just need to know what's the mean and standard deviation and is it normally distributed. The mean of P hat is P. This was very similar to when we said the mean of X bar was mu. Remember, that just meant that if we graph all the different P hats, they are centered at the population proportion, which means we're in the ballpark. We were not all overestimating, we were not all underestimating. So we talked about that before break. The standard deviation of P hat is a very ugly term because there's a radical. P times 1 minus P divided by N, you take the square root of the entire thing. When we do an example in a minute, the beauty of a video is you can pause and stop me whenever you want. When I calculate one of these, I suggest you stop the video, calculate it yourself to make sure you're okay with your calculator. Because again, many students mess this up. They forget to take the square root. They don't use the parentheses correctly. Lots of mistakes happen in that one term right there. On your cheat sheet, if you look, you will see it summarized like this. Okay. Looks like that on the cheat sheet. So I give that to you. But how do we know it's normally distributed? We do have criteria. Now, when we did X bar before break, there was one of two ways, and there was an or between those. The normality criteria for p hat is completely different, and there's actually two things, and they both have to hold. I'm going to erase now, so you can always pause me if you're not done taking notes. How do we know p hat is normal? Two different rules. N times p has to be greater than or equal to 15, and n times 1 minus p has to be greater than or equal to 15. There is an and in there. Both of these have to hold. Also, just to let you know, the 15 is not set in stone. Your book uses 15. Many books do. Some books use 10. If you are used to that from biology class or something, you are welcome to use 10. But in all the examples I do, I'm going to use 15. The good news for this topic is the process only goes forwards. It does not go backwards. So we're going to turn our p hats into z's, because remember, that's the only chart I have, right, is the z chart. How do we turn anything into z's? The way we've always done it. We subtract off the mean, divide by standard deviation. All right, let's do the first example. All right, and this is a very real example. It's about trying to do a poll either before the election or on election day to try to predict who's going to win. Sampling distributions, I don't know if I mentioned it, they're kind of fantasy land. They're fake. They're going to give you the population information, then they're going to give you the sample size, and then they're going to ask you a question about the sample. So, and that is all, again, what I try to summarize right here on this handwritten sheet. All right, so example 1. Anne is running for political office. Okay. We somehow know she is favored by 48% of all voters. This is what I mean by Fantasyland. They're letting you look into their crystal ball, and they're telling you that somehow they know that Anne is only going to end up with 48% of the vote. Just to make sure you don't overthink this, period. I'm talking as if I'm texting on my Siri. The other candidate would get 52% of the vote. There's not 3 candidates. I'm looking for a different color pen. So as soon as you see this, you can imagine they pretty much ask people, are you going to vote for Anne or not? Yes or no question. We can describe that as proportions. They just gave you the truth. They just gave you the P, which is 0.48. So that's what you get from that sentence. I'm going to keep reading my problem. A polling group will sample 500 voters. A polling group will sample 500 voters and use the sample proportion to estimate the population proportion. Makes sense? All right, what did they just give us there? They gave us the sample size. And again, on this handwritten sheet, I tell you, they're going to give you N, they're going to give you P, then they're going to ask you a question about P hat. So let's keep reading the problem. What is the probability they find more than 50% say they will vote for Ann, thus predicting the upcoming election wrong? What is the probability they find more than 50% saying they will vote for Ann? Making them think that Ann's going to win the election. Thus, that's why we say they predicted the election wrong. Because remember, we already know from the given information that Ann is going to lose because her opponent is going to end up with 52% of the vote. And the question is, what's the probability that I find from my sample more than 50%, meaning I think that Ann's going to win, meaning I've predicted it wrong? This has happened historically in the presidential election. One of the networks tried to predict the president probably at about 8 p.m., and at 10 p.m., they had to come back on and say, wait, it's too close to call. We don't really know who's going to be your president. And basically, they had to hand count votes for the next month until we found out who was going to be the president. So this really is very real life. Let's see, question. So the question that they're asking, they have to ask a question about the sample proportion, about the p hat. They are asking, what's the probability our sample proportion is greater than 0.5. All right. Now, I certainly hope I have normality, or I don't have a problem to do. So we have some scratch work to do. We need to check normality. Is p hat normal? Okay. N times p greater than or equal to 15. I can estimate that. That's about, it's definitely over 200. You can put that in your calculator if you're not good at estimating. And then N 1 minus P greater than or equal to 15. They both have to hold, and they do. That's over 250. So I'm good there. I know P hat is normal. Okay, I'm going to erase and keep going up at the top. Right. So I know p hat's normal. I know the mean of p hat is p. I don't know if I mentioned it earlier, but we've been doing this since test 1. Proportions are numbers less than 1. So that's why I immediately at the beginning turned the 48% into 0.48. That's the mean. Standard deviation is that yucky term. These standard deviations get very small. Sometimes I'll keep 5 and 6 decimal places. This one is 0.02234. You should definitely check that to make sure you can get that. All right, so see, these are the problems. This video is the topic you hate on test 3. The rest of the topics are pretty good. I lost my train of thought there. I know what I was going to say. We've done so much work already, but you have to remember we haven't answered the original question. The original question was that. Okay, we are ready to get z's. Sorry, I thought my video had cut off. It has not. All right, back to where I was. We got to turn the p hat into a z. How do we get z's? We subtract off the mean, divide by standard deviation. That's how we have calculated z-scores all the way back to test 1. That turns out to be 0.9. It was really, I think, 0.899 to 2 decimal places. It's 0.9. See, I've stayed organized. I've carried around my greater than symbol. I go to my z-chart. I look up 0.9. I see 0.8159, but since it's a greater than problem, I have to subtract from 1. So my final answer is 0.1841, or 18.41%. And that is very real life. That is high. Over 18% chance of predicting an election wrong. The only thing that maybe is not complete real life on this is all political polls, particularly at the national level, is based on a sample size of 1,000. This was kind of low at 500. If you redo this whole problem using an N of 1,000, you'll actually see this to be about 10%, which is still high. No network wants to risk predicting an election wrong if there is a 10% chance that they will do that. That is way too high. So that's the answer. We have another whole problem to do. All right. Problem number 2. This one's quite trickier. It's got some weird stuff in it. It will prep and help you do 2 of the harder problems on handout 9. So this is about a very rare chromosome defect. I shortened up the original problem. A defect occurs in 1 out of 200 men. Then it says we will sample 100 men. So let's talk about what they've given us there. They didn't somehow measure and tell us the lung capacity of men or maybe their blood pressure or anything like that. They pretty much went around to men and said, do you have the defect or not? It's a yes-no question. It is camp proportion. It is not a mean problem. It's a proportion problem. They told you the truth. A defect occurs in 1 out of 200 men. They just told you that the P, the population proportion, is 1 out of 200. Remember, they can give you the information in fraction form. A fraction just means to divide. So if you want to see it in decimal form, put that into your calculator and you'll see that the P is 0.005. Of course, your N is 100. See how they give you the P and they give you the N. Part A. It asks, is P hat normal? Is it normally distributed? Let's check. N times P greater than or equal to 15? Well, no, because that's just like 0.5. No, it's not normal. Okay, well, I'm not doing anything with that question. That's why they go on and ask part B. What is the smallest sample size we can take to make P hat normal? researchers know statistics, but go with me here. Let's say a researcher knows they have such a rare disease, and they intuitively understand that they're going to have to take a larger sample size just to get probably 1 or 2 men with the defect in there. So they are very interested in doing good statistics. So it makes sense that they would ask this question. Now, of course, I could be sarcastic and tell them, oh, go sample 1 million men, I'm sure that's fine. Well, yes, but I don't have the time and money to sample 1 million men. So that's why it's worded like that. What is the smallest sample I can do where I'm still doing good statistics? So we are going to use our normality criteria in a bit of a backwards way. Remember, NP greater than or equal to 15, and then N1 minus P greater than or equal to 15. We're leaving the n's. We want to solve for n. So P is 0.005. 1 minus 0.005 is 0.995. Solve for n, divide both sides by 0.005. We get 3,000 here and 15.07 there. You do get 2 answers. We're not done. Now this is where it gets tricky. A lot of students think, well, it said smallest, then the answer must be 15. But think about it. That does not make sense. Up here in part A, we had already decided that 100 wasn't big enough. How could 15 be big enough? So the answer is the 3,000. But here is the rule you have to remember. You pick the largest, and that's an and symbol, round up if it's any decimal. We didn't end up with a decimal here, but I think there is one on handout 9. This is the only time that I give you a special rounding rule, period. I have to stop doing that. I know y'all are laughing at me. If we had 3,000.2, we would round that up to 3,001. All right, there is a part C, so I'm going to erase this. So, same question, part C. When sampling 3,000 men, what is the probability the sample proportion will be within 0.001 of the population proportion? That's very awkward wording. We really like the first example where it said something like more than 0.5. That was super clear, right? This is very unclear, but we'll get back to that in a minute. They say that we're going to sample 3,000. Well, I do already know from part B, that means I'm okay on normality, because part B had me test for normality, and I decided that 3,000 was the minimum, so I'm fine for normality. Let me do some of my scratch work. I know p hat is normal. The mean is p. The standard deviation is 0.005 times 0.995 divided by the 3,000. This number gets really small. It is 0.001288. Something like that. Remember, this is the mean. This is the standard deviation. I need those two pieces because I'm about to figure out what are they asking me, which also means I'm about to calculate z-scores. Where's the question though? Okay, within. We learned what that meant a while ago. It means to jump up and jump down. So I'm supposed to be jumping up and down that amount from what? From the population proportion. The population proportion is 0.005. So apparently I'm supposed to be jumping up and down. If you do that, this is the question that they want us to figure out. And you can kind of see that makes a stuck in between problem. I got to get two z-scores. How do I get z-scores? I subtract off the mean, divide by standard deviation. Subtract off the mean, divide by standard deviation. Now think about it. You jumped up and down by the same amount. These z-scores should absolutely be the same z-score. It's just one's going to be positive and one's going to be negative. Some of you mess this up on test 2. Remember on the stuck in betweens, you do not subtract the z-scores. You look up the z-score. When you look that up, you get 0.7823. And then you subtract the two areas. When you look negative 0.78 up, you get 0.2177, which will give you a final answer of 0.5646. This is the hardest problem. Pause me if you're not done writing because I'm going to erase. This problem, so here's some random comments now. Example 2 will really help you on handout 9, number 2, and number 8. That's more of an FYI. Your homework is handout 9, numbers 1 through 8, and in the module test 3 handouts, do the review day handout, and there is an answer key. All of this is for sampling distributions. So at this point, the one day before break in this video is half of your test 3. This is the hard material. You need to start this stuff now and do it many, many times. Also, that way you can get my help online, of course, over the next couple of weeks if you need it. Part of the sampling distribution and these homeworks is always going to be when you read a question, are you going to be able to tell basically if it's an X bar question or a P hat question? My two camps I keep talking about. That ultimately has to be the very first thing you decide because the formulas and the process are very different for each. You don't know if you're going to be here or if you're going to be here. So through that, you'll be practicing it. I'm looking at my random comments. Yes. All right, so that concludes our first video. Hopefully it is at least acceptable instead of face-to-face lecture. Remember, you can watch the video as much as you need. Practice the homeworks. Don't let these wait a week or two. Get really good at this before you start into the new topic, confidence intervals, which will start on video 2.